morning, guys. How are you doing? I hope that you're all doing well and staying healthy. You're doing a great job so far, and we're getting down to it. We're almost at the end. This upcoming unit is a really fascinating unit. We'll go nice and slow, and there's some really interesting patterns that we'll be able to pick out as we progress through it. This class is one of my favorites, or at least this activity. We came up with this is my second year doing it, and I really, really like it. So hopefully you'll get something out of it as well. I actually had a student email me last year saying that he's using the thing that we did that we're going to do today and the next couple of days. He used it in his first in the geophysical class next year. So hopefully some of you will be able to reuse this again next year. So first off, let's take a look at a model. If our Earth were the size of a globe, which is about 30 centimeters in diameter, it's about the length of one ruler, how big would the sun be? Would it be like a beach ball or a basketball or something bigger than that, medicine-sized ball? How far away would the sun be? Would it be 10 feet away, 20 feet away? And how big would the solar system be? So if the Earth was the size of a classroom globe, could you fit the entire solar system in your house or in a classroom or in a football field or in the town of New Canaan? How big would these things have to be if you shrunk the Earth down to 30 centimeters? Well, what we're going to be doing is creating a calculator, an Excel or Google Sheets calculator that allows us to manipulate the size of a model Earth and scale the rest of the solar system relative to that model Earth. And that's that'll take a couple of days, but it's a really interesting calculator once you have it down. So let's talk about how far away the Earth is from the Sun to begin with. The Earth's orbit isn't perfectly circular, but on average, it's about 93 million miles away. It's about this far, 93 million miles, and Mars is about one and a half that distances, so close to probably 200,000 kilometers, 200 million kilometers away. These numbers get out of control very quickly because 1 mile is such a small distance when it comes to space. For example, right now, in the time it takes me to speak for 1 second, Earth will have moved 18 miles in its orbit around the sun. So we're traveling at incredible velocities. Um, and it just doesn't make sense to start using miles and kilometers when we're talking about distances in space. So instead, we use something called the AU, which is called the astronomical unit. And it is equal to the average distance of the Earth to the sun. So our distance is equal to 1 AU, and the distance to Mars is 1.52 AUs, 1.5 AUs, because it's a little bit farther away. Let's take a look at this model. This is a model of our solar system you might see in a textbook or in a poster or something. And when we're looking at it, um, it's actually a very, very poor model. Nothing is to scale, is what's wrong with this model. The only thing it does well is it shows the names and the relative locations of these planets. So it has the order right. Mercury's first and Neptune is farthest out. And it does give some sense of how big they might be, with the Earth being smaller than Jupiter, but it is much smaller than this. Jupiter is much, much bigger than that. So it doesn't really get the sizes right. It doesn't quite get the distances right. It just has the order, the relative order. Maybe it has the relative sizes, but I'm not even too sure about that. It looks like it might have the relative sizes. Jupiter is definitely the biggest planet, and Mercury is the smallest. Well, Pluto's not a planet anymore. But for the most part, it's not that great. So this model is a bit of an improvement. What it does nicely is it kind of shows you how far away each planet is from the other ones. So you can see that this is Saturn's orbit, and the next one out, Uranus, is very, very, very far away, and then Neptune is even farther than that. But I don't even know if this model is perfect. And then you can see on the inner planets, they're actually kind of bunched together in this model. So for that reason, it's not that great because you can barely tell what's going on down in there. This model, what does this do well? Well, and what does it do poorly? Well, what it does nicely is it gives you the sense of the size of each planet, right? So here we have Earth, and that's Jupiter next to Earth. So Earth is quite small. Then the sun. I mean, look at how big the sun is. You can barely even see how it's arcing, how it's changing right there. And then it's got Uranus and Neptune about the same size, and Venus and Earth at about the same size. So this one gets the sizes right, but it does not even attempt to show you the distances between them. So basically, all this is to say is that modeling the solar system is very hard to do in a visual way. because you have to sacrifice some kind of information. Either your planets won't be to scale, their sizes, or the orbits won't be to scale, the distances between them. So instead, we're going to turn to a mathematical model to help combine these relationships, and we're going to be using Google Sheets to do so. So just to kind of refresh what you're doing here, this is a status bar. These are your tabs. You can change between tabs down here. You'll be working in one tab. Up here is a formula bar. You really want to be paying attention to that because that's where you'll be seeing all the formulas. So you can edit your work in that formula bar. And then across the top are the columns. That's A through Z. And then down the side are your numbers. So if you wanted to find cell C12, you'd go to C and then come down to 12, and it's this one right there. So just make sure that you're aware of how to find the different cells using this kind of alphanumeric identification system. All right, so what we'll be doing for the next couple of days is filling in a mathematical model or completing a mathematical model of the solar system. Make sure you follow the directions very, very carefully. I would highly encourage you to print out these directions, double-sided to save on paper if you can. You can do it, of course, on a computer screen, but it's hard to cross off steps and to really follow your work. So I would encourage you to print them out and have them at your desk for the next couple of days. If just one part of the code is incorrect, the entire calculator doesn't work. So it demands perfection. There's really no way to say it. Your model has to be perfect just to get it to work. Otherwise, it won't work. So we're going to move slow. And of course, we can be flexible with timelines. I'm not too sure. Usually this takes 3 days in class to do. So I don't know if you'll get through it faster because there's fewer distractions, or if you'll have more questions and it will take longer. But my pacing, at least initially, goes something like this. Monday, today, I just want you to fill in tables 1, 2, 3, and 4. 1 and 2 is just filling in data. There's no real calculations involved or no thinking. It's not too tricky. 3 is nothing. It's just one number. And then 4 is just one calculation. So you should be able to get through 1, 2, 3, and 4 if you follow those directions closely. On Tuesday, we'll complete the table. We'll complete the Excel spreadsheet, which is tables 5 and 6. On Wednesday, we'll apply this calculator to different scenarios and we'll actually see it in action. And then on Thursday, we'll kind of address any issues that come up, and there's some optional level 4 work that you can do. But again, this is flexible. We may only get through table 1 and 2 today. And if that's the case, that's fine. But this is what I'm thinking should work out. All right, so let me show you what the finished product looks like so you can see where we're going with this. Here we go. So this is our finished product. So we have tables 1, 2, 3, 4, 5, and 6. Tables 1 and 2 are the actual measurements of the planet sizes and the distances from the sun, which is table 1, and the size of the planet, which is table 2. That information is given in both astronomical units and kilometers over here. And then for the size of the planet, that's in kilometers and miles. Uh, Size 3 is the important one for once the calculator is totally finished. So in this table, what you'll do is you'll input information into this yellow highlighted box. You'll input the size of your model Earth in centimeters, and then everything else will be updated for you. Size 4 is going to be the ratio. This is what's going to determine this will be our relationship between our real actual measurements and our model measurements. So it's having this formula in table 4, which is F11 divided by I11. Doing that ratio will allow us to convert all this information into model information. So table 5, this is the distance from the sun at the various scales. That information is given in several different formats. You can get it in centimeters, feet, yards, and miles. And then table 6 is the size of the planets in different formats. So for example, let's say our planet Earth, let's change it to, let's see, a meter. A meter is 100 centimeters. So we're actually already at that thing. So if our planet Earth was 1 meter wide, then it would mean that Mercury would be about 2.85 miles from the sun, and Earth would be 7.31 miles from the sun. And Mercury would be 1.25 feet wide, and then Earth would be 3.28 feet wide, which is equal to 1 meter, which is 100 centimeters. So let's change this. Let's go to half a meter. Let's say that our Earth, we change the size of our Earth to 50 centimeters. And as you've noticed, all that information updated, right? So when you change this number, all of the information in table 5 and table 6 updates because now it's being passed through this kind of unit converter, and it's changing the sizes and the distances of our model. So at half a meter, um, our Mercury goes to 1.42 miles away. So if you kind of stretch out the length of your arm, we'll say is about half a meter. If the Earth were that big, then the Earth would have to be 3.65 miles away from the sun in order to fit that model. So you can see how this model is pretty powerful in terms of giving some approximate information about how big our solar system is. Okay, so the one thing again, I'm going to go back to this sheet, this page right here. I cannot stress enough to make sure you read the directions carefully. Um, Cross them off as you go through them and just follow them to a T. Okay, good luck and email me if you have any questions.